Welcome to pattern analysis. This is our first lecture. I will first give a brief introduction and then we talk about actual methods. This very first slide deck is here on our first sampling method, but we will come to this. So to begin, you are probably familiar from the pattern recognition class with the so-called pattern recognition pipeline. It's just a schematic perspective on how to do the data processing that leads to an automated classification. Let's quickly go through it. So there is some data in the world, maybe a scene, I don't know. You take a picture, and this is a sampling process, you can say, like where you direct the camera to the way how it records the image in detail and so on and so on. And then you have the digital image. This digital image usually is subject to some form of pre-processing. Maybe you cut out regions of interest, like in this case, the face. Then some feature extraction is done. If the goal is, for example, to recognize the face, then it may make sense to recognize facial landmarks and to use this reduced representation then for a classification task. So classification is done by a classifier. The feature data, this is a vector x, and the classification, this is f of x. And then the classifier says, oh, this is, I don't know, this is a face, or this is a male face, or this is person A. Whatever the classes are that the classifier distinguishes, we just say this is Y, the class that we decide for. And you're also familiar from the pattern recognition class or some other class, probably with this fundamental assumption in machine learning, that if you have a feature representation that somehow makes sense, so that is good in a way, no? Then similar objects, like with whatever goal you want to achieve, similar objects are mapped to similar feature representations, so to similar locations in space. No? So this is the basic assumption, and then you can say, okay, like whatever is close to each other in my feature representation, this should be something, should be the same object or should be the same class that I want to assign. And if we talk about this like classification or regression business, then we're talking about supervised methods. So the training of classifiers, this is a supervised process. We have training input xi, training data, an associated label yi, and then we can tune the classifier such that it can make that prediction also for inputs that were not part of the training data. So this is all part of pattern recognition. In pattern analysis, we are more looking in the direction of unsupervised machine learning. More specifically, we look at generative models. Unsupervised machine learning works without labels. That means it only operates on data xi, but there's no associated label yi. We will have exceptions to this. We will also have labels in pattern analysis from time to time, but just to set the tone a little bit for many methods that are going to come. Okay, now another very basic considerations is the relationship between data and distributions. And by distribution, I always mean like probability distributions. Let's look into this. So an observation is an actual data point. Yeah? It's a specific instant of data, a data point. This can be a scalar value x. In that case, it shouldn't be bold-faced, or it can also be a d-dimensional vector x. This depends a bit on what the data is. For example, if the data is an image, you would say, okay, this is a high dimensional input because you have so many pixels. And so every pixel would be a separate entry in that data vector. That would be a d-dimensional vector. Now, if we say we're interested in statistical learning, the whole point about this, let's say, empirical type of machine learning that we are doing here in pattern recognition, pattern analysis, then we require many observations. And in order to draw some conclusions from these observations, which is called inference, the data has to be mathematically abstracted to distributions. Yeah? So you say, okay, I have 100, 200, 1000, whatever number of observations, and I somehow need to put them somehow in groups or to somehow summarize them. The way to do this summarization in a mathematical way is to say, this is a distribution. Yeah? And this is why distributions matter so much in pattern analysis. So, taking that assumption that all sets of data are from distributions, form distributions, then you can turn this perspective around and you can say, okay, so this means if I'm making an observation, if I'm observing a data point, for example, by taking a picture, then this is actually a sample, this is one instance from an underlying distribution. Maybe I don't know this distribution, this underlying distribution. This is a different topic, no? But in principle, so we have this duality that we say observations and samples, these are the real world artifacts that we have. And the distributions, these are the mathematical concepts that allow us to summarize this data. Yeah? So an observation is something that I actually get from the real world. A sample would probably be a draw from that distribution, but I use these two terms interchangeably throughout the lecture, so I'm not really distinguishing them properly, but just to your information. Okay, so all observations are assumed to be samples from an underlying distribution. And then we have the notion of a machine learning model. A machine learning model is usually like a mathematical function or something that represents this underlying distribution. This can be either implicitly, so if you think about a classifier, this is oftentimes not really a distribution that is modeled there, but it only models the boundary of distributions, that it says, okay, from the left here, this is class 1, and on the other side, this is class 2. Or you can also explicitly model these distributions. We will do this a lot in pattern analysis. Yeah? And usually, since I was mentioning this like true global distribution, and then we take a picture of it, the representations that we actually form in the computer, these are usually simplified forms of these real-world distributions, because how could we possibly model the whole world? No? Okay, but this is a different topic. So now if we also introduce the notion of generative models, so generative models are those models that collect observations into a distribution and then also allow or offer to generate samples from that distribution. So we have both perspectives united in generative models. And this is what we will be discussing quite a bit also in this class. Let's talk a bit more about inference. So what is inference? Inference very basically is just a process of drawing some conclusions from inputs with the help of some logical rules. And everything that we do, of course, is in the context of statistical learning. So this means inference is something that is performed on random variables. and their associated probability distributions. Yeah? So all logic is not a logic in the sense of theoretical computer science, but it's logic in a Bayesian statistical way. Yeah? So this means we operate on random variables, they have associated probability distributions, and the rules that we have, these are the operations that you most likely learned in some earlier statistics class. So first of all, we have the notion of a joint distribution of two variables. Then we have the notion of a conditional distribution of two variables. So here we have the conditional distribution of x given y. And so these are actually not rules, this is vocabulary, we can say. Here's an actual rule, so we can form the distribution of x, p of x, by marginalizing over all instantiations of y in that joint distribution. So p of x is the sum over all instantiations of y over the joint distribution of x and y. Then we have the product rule. So a joint distribution of x and y can be formed by multiplying the conditional distribution of y given x with the distribution of only x. So yeah, I leave it like that. And we have a Bayes rule, super famous and super important and so on, that says that the conditional distribution of y given x equals the conditional distribution of x given y times the probability of y divided by the probability of x. And this is a direct application of the product rule. So if you extend this to the other side by a decomposition, p of x given y times p of y, then you can direct from this, you can directly form Bayes rule out of this by dividing by p of x. So this goes here to the bottom, and there's Bayes rule. No? Okay. So far, so easy. Why is it so famous in the context of machine learning? This is because of the interpretation of x and y. Yeah? So x here is a distribution of observations, can be class-specific observations, so no? And y is the associated class. And then it makes sense in view of talking about inference, because then you can say, okay, if I have a likelihood, the likelihood that I would be seeing a sample x, knowing that actually the class y is the generating process, I have to moderate this a bit with the prior probability that y could be the generating process at all. Then I would have to normalize this by the probability that I would be seeing a data point like x at all. Then I can turn this around and can say, well, okay, from this I can conclude that the so-called posterior is the distribution of possible classes, and the possible classes given input x. Yeah? So then I have something like 60% it's class 1, 20% is class 2, 15% it's class 3, 5% it's class 4, something like this. It's a true distribution. It's normalized to 1 thanks to division by the evidence. These are very basic things, and I don't want to super bore you, but I mean, you saw it probably in our meeting. We have a very broad audience, different backgrounds, and so on and so on. Like, whoever feels that he or she wants to catch up on these things a bit more, please have a look at the book by Bishop that is linked in StudOn. section 1, 2, 3. Yeah, so there's a bit of a recap there. We are also going to talk about this in our joint meeting. And it's important, we will use this a lot in pattern analysis. Another notion that we need, parameters and hyperparameters. Parameters are coefficients of a model that are somehow defined or adjusted, calibrated, calculated, whatever, during the training of a machine learning model. Yeah? So here's a specific example. Consider a d-dimensional input x tilde. So 1 is a constant here for technical reasons, and then we have d minus 1 inputs here, the dimensions of x. Linear regression then uses the d parameters beta 0 to d minus 1 to define a d-dimensional hyperplane. This is a repetition again from pattern recognition. You probably noticed this. And then what linear regression does is it calculates an inner product of input x with the hyperplane, and this leads to the prediction y. So y equals beta transpose x, which expands to a sum over these d dimensions, where every dimension individually is multiplied together and added up. You can also say, okay, these d dimensions, these are actually not dimensions with different input data. These are just polynomials or monomials, of higher degree of the same input variable, scalar input variable x. It's just a variant. You can mix and match this. And then you have your linear regressor. Okay. I don't want to talk too long about linear regression, but the important point there is that d is a hyperparameter. So that means it is something like a parameter, but it's a parameter that determines how many parameters do we have. So it's a parameter that somehow parameterizes the choice of parameters. So if we have a larger d in the context of linear regression, if we think about this basis expansion here, it means we have a higher degree polynomial. So we can form a more complex shape. So it's more complex, it's more flexible also in a way. But if, for example, the data on which we are calculating this, the input data, if there's a lot of disturbances in there, then it might be the case that we are also learning, unintentionally, we're learning structure that we don't want to learn. So in a way, it's also less robust, you could say, and we're going to talk about this aspect more in the future. So the associated task here is the so-called model selection problem. That we say, okay, there's a universe of models with hyperparameter d equals 1, d equals 2, d equals 3, and so on. The model selection problem is to find hyperparameters that tunes the model complexity best for the level of detail that we are seeing in the data. We talk more about this in the future. Sampling from a PDF. We already said, okay, we have observations being samples from a PDF. What does that mean? So the process of sampling means that we are drawing one instance, so one sample from a probability distribution. So this can be very simple. Here's a simple example. You can say I'm playing dice, I'm throwing a fair dice, and this gives me a sample from a uniform categorical distribution with 6 categories, namely the numbers 1 to 6. Okay, simple. A sample from a d-dimensional Gaussian distribution around some mean vector mu using some covariance matrix sigma is also fairly simple, but but more complex than throwing dice. Main difference to throwing dice, certainly apart from the dimensionality, is that this is a continuous distribution, yeah, and the dice were a categorical distribution, whatever. Continuous distribution. Continuous distribution means there's not a number like 6 that we have in terms of possible results, but infinitely many. Still, Gaussians are simple in that sense that there are special functions that offer closed form equations for sampling from a Gaussian. And we are going to talk more about this in the future. However, there are also very complex samples. We will talk about Markov chain Monte Carlo sampling later. But also, if you think about your immediate exposure to generative systems that sample, then you could just say a ChatGPT response is a single sample. But still, it's rather complex in the sense that it consists of many words, many sentences. So it's a rather large sample. Yeah. Okay. But in any case, to make this this concept of sampling a bit more concrete and how it can be done, let's have a look at a basic sampling algorithm to begin with, the so-called inversion sampling. So, here's an idea. First of all, it's only good for distributions that can be integrated. So consider a categorical distribution or a continuous distribution that is easy to integrate. Yeah? Then you can calculate a so-called cumulative density function, CDF, and let's just call this cumulative density function P of z of x. Yeah? The definition is super simple. We calculate an integral from minus infinity to value z, and this is P of z, over the input probability density function P of x. So if you look at this, you can say, okay, from my statistics class in 2000 whatever, I know that z is the pzth quantile of the probability density function. And that means that a uniform sample drawn from P of z, for which we do have some implementation in our operating system or whatever machine learning library. So if we draw a uniform sample, check PC where it at which location it intersects the graph, then this corresponds to a random draw from P of x. Because, and this is why it has this name, P of z inverse is approximately, or is essentially proportional to P of x. So what does that mean? Here's an example. So we have P of x here. It's a bit more likely here for larger values of x. It's a little bit of a lower probability mass here for smaller values of x. And now, if we look at the associated cumulative density function, what we are seeing here, if we have less probability mass here, it's a more shallow increase in the CDF. If we have more probability mass over here, we have a steeper increase in that function. Yeah? Okay. And now we said, okay, let's draw a uniformly distributed sample and align it with P of z here. So here are 3 example samples. Let's check where it intersects this cumulative density function. And let's have a look at the x-axis here. Here, here, and here. These are the actual draws from the original distribution that we had here. And it's not a coincidence that we are seeing more samples here in this area where we had a higher probability mass, because from the increased steepness of the CDF, it's more likely that we are hitting this part of the curve rather than from the flatter section here. So the algorithm in a nutshell: split the domain of P of x into discrete bins, enumerate the bins. On these bins, calculate the cumulative density function P of z of P of x. Draw a uniformly distributed number u between 0 and 1, because the CDF is always between 0 and 1. Sorry, I'm jumping. The sample from the probability density function then is the lowest, for the smallest P of z that is larger or equal than u, than this randomly drawn number, we are interested in the coordinate c. No? So this is a bit of a complicated expression, but essentially it formulates when you intersect the CDF, take that value. But for a categorical distribution, for example, you will maybe not exactly intersect it, so you have a bit of a jump between the categories. This is what it expresses here. Okay. So inverting a uniform draw from the CDF gives a draw from the original distribution P of x. This is essentially the sampling algorithm. So when implementing this, as mentioned earlier, it works quite well for categorical distributions, and like without a big problem. It can also be well applied to analytically integratable continuous distributions. And for all other distributions, I mean, it can also work, but we have to solve two problems, and they can be a bit inconvenient depending on what our situation is. So one thing is we somehow need to discretize the space, because we need to numerically integrate somehow the PDF. And then we need to obtain these values P of x for each bin. And depending on how we have that density represented or so, this can be easier or harder. So these are the two problems, and more specifically for the discretization, like what is a good bin size for discretization? It's not really clear. The second question is, I mentioned it already, is it really feasible to get this P of x for every bin? Yeah, we can discuss this probably later. No? And what we will also do later is to look at more advanced sampling strategies in a couple of weeks. So the second topic for today is non-parametric density estimation. Density estimation estimates a probability density function from observations. So we have the sampling now, that we draw a sample from a distribution. Now we have the other direction, that we say, okay, there are samples or observations, and we want to create a probability density function out of this. This is not exactly new. We already know from pattern recognition the so-called parametric density estimation. The idea there was to use a parametric function model, for example, a Gaussian or some other function with not too many parameters ideally, and then either use a so-called maximum likelihood estimator or a maximum a posteriori estimator in order to fit these parameters. What is the idea? For the maximum likelihood estimator, one says, well, okay, I need a model expressed through the parameters theta that gives me a good agreement with the n observed data points that I have. And specifically, I choose those parameters that give the best agreement with these data points. So this is a maximum likelihood estimator. Maximum a posteriori is almost the same. It just takes the prior into consideration. So it says, well, okay, I have a likelihood here again that I'm looking at parameters that explain or that somehow come to a good agreement with the observations, the n observations that I have, but I'm moderating this by a prior distribution over these parameters, such that, for example, I can influence this model in a certain direction, that I say, okay, if there are, for example, higher order coefficients, lower order coefficients, that I say, well, try to get a good agreement with lower order coefficients and maybe set the higher order coefficients to 0 if you can. So this would be maybe a typical way of formulating a prior, for example. No? Okay, so I don't want to talk too much about this because you covered this in pattern recognition, but what you need for parametric density estimators is some agreement, a good agreement between the observations of the data and the associated function representation. So you need some idea, okay, this should follow a Gaussian distribution, and also empirically I see that it behaves like a Gaussian, so all is good here. If you don't have this, maybe your data just doesn't behave like a Gaussian or so, then you need some other plan. You can say, okay, I patch this with a Gaussian mixture model or so. Yes, you can do this. We will talk about this also later. But another possibility is to use a so-called non-parametric density estimator. So non-parametric density estimators, they offer more flexibility when it comes to the choice of functional representation. They're more indirect at this point. So they only require some form of a complexity bound. And so to say, like, how much detail should I put in this density? Let's have a closer look. So here's a very simple, you could almost say dumb, non-parametric density estimator, a histogram. So a simple non-parametric baseline is to create a histogram of samples. Histograms are super popular. So I don't want, by saying like a dumb method, I don't want to put this in a bad light. They are super useful. First, they are good for a quick visualization. Second, they are cheap for many samples residing in a low-dimensional space. They also have their limitations. So one limitation is at bin boundaries there can be discontinuities, and this can be something that is disturbing depending on what you want to do. I mean, you can smooth this out also if you like, but this is one issue to address. And the second issue is that it doesn't scale very well to higher dimensional spaces. If you have an 800 dimensional feature space, the 800 goes in the exponent of the number of bins per dimension, so it's really creating a problem. So if we say we have 16 bins per dimension and then 800 dimensions, then it's really terrible. Okay, so this is not a possibility that we have. But other than that, histograms are useful. However, the number of bins that we choose per dimension, this has a great influence on the representation that we obtain. And here's a picture from the book of Bishop showing this for an example of 3 bin sizes. Yeah? And we see the resulting, so here in green is plotted the underlying true density that generated these samples. In blue we see in the bins, like the histogram bins of the observations drawn from that underlying density. You know? And we see if we take a very coarse binning for bins here, then it just looks like a ramp, no? The distribution of samples increases, which appears a bit undercomplex compared to the underlying distribution, no? Here this I don't know how many bins these are, 5, 6, 7, 8, 9, 10, something like 15 bins, I don't know. It looks better. It almost looks a bit like the underlying distribution. But then if the number of bins is further increased, we lose this insight again. Yeah? So empty bins just by chance happen to occur. We also have this up and down of bins here, which kind of invents structure that is not part of the generating process, but more an effect of our sampling process, that randomly drawing from a distribution just leads to an imbalanced representation of these samples. No? And this is a very fundamental problem that we will have in many methods. Yeah? So too few bins miss important structure, and too many bins, I use the word hallucinate, but sort of, you could also say like overfit or so, no? to these input samples. But essentially they are pretending that there's some structure there. No? So you have some variation here in these bins that is not really justified from the underlying generation process. Yeah? And this is the problem. No? So for the histograms, but also for all other methods that we look at, but for the you must tune somehow these hyperparameters to the data set. So for the histogram, the hyperparameter is the number of bins. Yeah? Okay. There are alternatives of non-parametric estimators. There are alternatives to the histogram approach. So specifically, we will look at so-called kernel-based density estimators and nearest neighbor-based density estimators. So these are also non-parametric density estimators, but the main difference to histograms is that they define the density implicitly. What does that mean? So it means that you don't get a global representation like in a histogram where at will you can just check every bin. You don't get such a global representation of the distribution, but instead, if someone is interested for a location X, what is the density at this location, then quite ad hoc, they calculate a density estimate for this location. So it's like, you can think about this like an interpolation method, that if you query that spot, then it looks at the neighborhood and says, the density here is so and so. Hmm? This has an advantage, so it avoids these discontinuities that we just mentioned here at histogram bin boundaries. So if you have an input X and look at the density P of X, and you have an input just next to it, just moving a little bit, and look at the density P of X plus epsilon, then at a histogram it may be the case that it jumps. No? Here with these like local interpolators, it's not so likely, depending on how they are done. So this certainly is an advantage. No? And there are further opportunities for optimization. Maybe we are going to talk about this in one of our meetings. On the downside, the lack of an explicit representation of the distribution limits the applicability of these estimators to cases where local density estimates are sufficient. No? We can also discuss this later. So how does it work? The beauty of this is they share a joint mathematical framework. At least the underlying basis is the same. So let's have a look at this. So P of x shall be a probability density function, so x undefined, like unspecified, shall be a probability density function in a d-dimensional space, and R shall be a small region around x. So x now is a specific input. So the probability mass in that region R is just an integral over that region of P of x integrating over this space x. Now we have two contradicting assumptions. Assumption number one, there are many points in this region R, many observations, data points. So we can just calculate a relative frequency to obtain an estimate of the probability mass in that region. So we take the number of points in R, which we abbreviate as K, and divide it by the total number of points in the whole space, N. The second assumption that we're making is that this region R is small enough such that the distribution P of x doesn't significantly change. So it's approximately constant in that area. So if we evaluate this integral over this region R of P of x dx, if this is constant, then if P of x is constant in there, we can pull it out of the integral, which rewrites to P of x times the volume of that space. So it's not really realistic that this space is super small and at the same time we have a lot of data in that space. So take this with a grain of salt, but let's just put it together in one equation. Then we can equate these two. We can equate these two assumptions and can say, well, P of x, which we took from the second assumption, equals k divided by n, which we took from the first assumption, divided by the volume, which again comes from the second assumption. And this equals the total number of points in that region divided by the total number of points in the whole space times the volume of that region. And this formulation can be used as a basis for the kernel-based density estimator and for a k-nearest neighbor-based density estimator. Let's have a look at the kernel-based density estimator first. This is the so-called Parson window estimator, sorry. So the idea for the Parson window estimator is to fix the volume of the space and to have variable, like depending on what we observe, the ratio k, so number of samples in that region, divided by n, the total number of samples. So the d-dimensional Parson window kernel function, called also a box kernel, is defined like this. K of u is some normalized input here, is 1 if every dimension, each of these d dimensions, has an entry that in absolute is lower or equal than 1/2. Yeah? So this is why it's called a box, because, let me draw this really quickly. If we have a point here, so it checks, is it within minus 1/2, is it within plus 1/2, and this for every dimension. So if we have, for example, 3 dimensions, it looks like this, it's a cube. Oh, screwing up the drawing, but anyways, you can imagine a cube, probably, hopefully. Okay, no? And you can easily generate this to d dimensions. This 1/2, it can be a fixed value here if you demand that the u, the input u, is normalized already or somehow scaled in size. And this is actually what happens. So if we look at the function, we have a total function where we go over all samples from 1 to n and evaluate this function k for position x. So we look at position x, look at the difference to the ith sample in our data set, and scale this. This is the scaling here in h by some factor. We will have to choose this factor later, so it's not for free, but we choose this the scaling factor, and then we can check, are all dimensions within plus minus 1/2? Then we return a 1 and count this, or we return a 0 otherwise. Yeah? And then to make this a density, we also have to normalize this, so we have to divide by the total number of samples. We will also have to normalize this by the window size, so 1 divided by h raised to the power of d. But here's our density estimator. And this gives a specific response for any location x that you desire. You just have to cycle through all n data points. Yeah, so the kernel removes much of this discretization error that we see in a fixed distance histogram bin, but it can still lead to blocky estimates. Yeah? If you don't want this for some reason, you can say, yeah, okay, box kernel is rather simple. No, maybe I want instead a Gaussian kernel. Then instead of a box function, I have this Bell function, smoother function. No. I have to replace, like I have to put the Gaussian here in my kernel function, e to the power of distance divided by window size squared, for example, no? Where h then acts as the standard deviation of the Gaussian, but then the estimates are smoother. No? You could also use any other kernel function that you like. You just have to make sure that the function always gives a value larger or equal to 0, and that it integrates, like in total that the value integrates to 1. So not a problem. The alternative is the k-nearest neighbors density estimator. So for this, let's have a look again at our derived equation for the density estimation. Number of points in the region divided by total number of points times the volume of that region. Now, the Parson window estimator fixed the volume and then checked which samples will end up in our window. The k-nearest neighbor does it the other way around. The k-nearest neighbor fixes k, so it always looks at k equals 3 or k equals 5 or so neighbors, and the volume, like the distance that we need in order to look for that value, to find these 3 nearest neighbors, this may vary, yeah, depending on how far away they are. So this means this is a constant, and v is variable in the k nearest neighbor. No? And the v then can be calculated from the distance of the k nearest neighbors. So the Parsons window estimator and the k nearest neighbor estimators are called non-parametric, but they are not free of parameters, which is a bit of confusing. So the observations are the parameters actually. Yeah, this is a bit surprising. So in order to say the density at point X is so and so, both estimators need to store all inputs, all samples. So all training data needs to be stored. And then we need to go through them in order to find either the 3 nearest neighbors or to find those samples that fall within the Parsons window. So this is why they are also called memory methods, because they need to memorize all data. And this is a bit of a minus point in many applications. On the other hand, you get a very nice local estimate ad hoc. No, that's the positive. So the kernel scaling h and the number of neighbors k for the k nearest neighbor, these are hyperparameters, and they need to be tuned for the task at hand. So let's have a look at the model selection problem. So how can we optimize, for example, the window size h, the k for the k nearest neighbor? If we directly optimize these hyperparameters on the training data, then the problem is that we will have that observation that the most complex model achieves the best performance. So the most complex model that we permit will be used to achieve the lowest training error. So therefore, the hyperparameters must be optimized on a held out part of the training data, which is called a validation set. I'm sure you heard this in another machine learning lecture. I'm just repeating it for the sake of completeness also. You know? So the way how it works is you train on a training set with different hyperparameters. So you do one training run for one model with hyperparameter A. You do one trainings run on that same training set with a different setting for the hyperparameter. Let's call it B. And then you repeat for all possible hyperparameters. For our Parsons window estimators, for example, this would mean you use different values of the window size, h equals 1, h equals 2, h equals 3. Are we sure that we should start at 1? No? Okay, so let's do h equals 1/2, h equals 1. Tell me, I don't know. You define a number of window sizes. For each window size, you train the model on the training set. You get different models out. And then you have held out validation data that has never been used for the training. And this is that you use to get the best performing, to determine which of these parameters is actually best. Yeah? So evaluate on the validation set. Okay. Now we're talking about statistics. So the validation set requires a certain size that it's statistically meaningful, representative. No? So sometimes in some application scenarios, the data sets are not so large. Yeah? For example, if we think about medical data, we have scans of patients. Depending on what scan of what body region or what disease or so we're looking for, maybe we don't have that much data. Yeah? Okay, so if the data set is too small to have a good statistically representative validation set, then you can always trick this together with a technique called cross-validation. So with cross-validation, you take the data that you have, split it into k partitions, and then train models for all these hyperparameters that we just discussed on all subsets of k minus 1 of these partitions, folds, sorry, in the phrasing of k-fold cross-validation. And then you check for each of these folds, for hyperparameter h equals 1, how did this hyperparameter perform on this subset? For h equals 2, it was like, how does it perform on this subset? And then you choose that hyperparameter that, when averaging usually or somehow else integrating all these subsets where this was used, if this leads to the best performance. Yeah, it's a little trick if data is limited. Okay. So let's look at the specific case of density estimation. So for supervised tasks, we know how to tune hyperparameters. For example, if we have a classification task, we can take a metric like the accuracy as a goal for the validation set to find the best set of hyperparameters. If we have a regression task, we can take something like an L2 distance, for example, for the prediction or can also be an L1 distance, no? To determine the quality of the hyperparameters. Now, if we look at the breadth of unsupervised tasks, then usually these concepts are not transferable. Yeah? Why? Because we don't have a target label, we only have the data. So if we don't have a target label, how could we possibly measure some distance from that target label, right? And we will discuss this more in the course of the lecture. However, in this case, with our density estimators, one can interpret them as regressors, which is kind of an exception from this. No? So one can see a density estimator as a regressor that predicts the density at location X. This is a continuous value, so it's a regression task, not a classification task, clearly. No? But this means we can use held-out observations to find the hyperparameters that best predict the density at location X. No? So let's use n held-out samples, xi, and then, like very generically, let's write the hyperparameters as a vector alpha. This is a bit of overkill. We only had the window size as hyperparameter for the Parson window estimator, and we only had k, scalar k, as hyperparameter for the k nearest neighbor. But anyways, whatever it is, let's call it alpha. And then we can just say, let's maximize the log likelihood of the density estimates for these held out samples. So we have the n held out samples here. P is the estimated density with our hyperparameter alpha, using our hyperparameter alpha. And we look how likely would it be with this density estimate to create observation xi from our held out data. We can take, you're also familiar from this from pattern recognition, we can take the log likelihood to make it numerically more amenable. So This means we have a sum here of the log of these observations, and we pick that set of hyperparameters that maximizes this log likelihood. Okay. Let me introduce informally this notion of bias and variance. I know that you discussed it in pattern recognition. We can expand this a bit in our joint meeting, formalize this a bit in our joint meeting. I think it's an important concept to be aware of for having a conversation about different models, different sets of hyperparameters, and so on. The motivation behind the hyperparameter optimization is to aim for generalization to new data. So that's the main point. And for kernel density estimation, you can say, what can possibly go wrong? Well, okay, it's a very simple scenario. So one possibility that can go wrong, your kernel is too large. So that means you cover somehow a lot of space with your kernel. There will always be a number of samples in that space. So, and if you move that kernel around to different locations, the numbers will not really vary. No? So all space is somehow covered with some probability mass, but the density looks rather uniform. So it does not really represent the structure. The other possibility is that you have a kernel that is too small. And in that case, if you are in an area where there are samples, then you get a decent density estimate, maybe even quite high. But if you just happen to be in an area where there's no sample, it suddenly drops off to a 0. We saw this in the histogram, that we had an empty histogram bin in an area where we were supposed to have a bit of a probability mass. So this is the problem with a too small kernel, no? That it sort of invents structure where there is none. And if there's such a thing like the optimal kernel size, which is, of course, a bit of a naive assumption, no? An assumption that you can fully explain the world and model it mathematically and so on and so on. Nevertheless, the optimal kernel size would represent the structure of the training data, and therefore would also offer an optimal prediction for unobserved data. Okay. And this whole conversation that we are having here about the too large kernel, too small kernel, and so on, this is an instance of the so-called bias-variance trade-off. By the way, you see there are always literature references here in the bottom. In particular, bias-variance trade-off here is in the book by Hasty, Tibshirani, Friedman, section 7. So for bias and variance in regression, this is the variant that Hasty, Tibshirani, Friedman essentially discuss through. There, the bias is the square of the average deviation of an estimator from the ground truth, and the variance denotes the variance of the estimate, so an expected squared deviation from the estimated mean. This is all covered in pattern recognition, but we will come back to it. Informal interpretation is high bias indicates model under complexity. We discussed this, like if our kernel is too large, then the density looks the same everywhere. High variance indicates model over complexity. The fit also models not just the structure of the data, but also the noise of the data, and noise in a very broad sense. No? All types of data inaccuracies and sampling randomness also, which strictly speaking is not noise, but a higher model complexity, so more model parameters, by tendency lower the bias and lead to a higher variance. And we will usually not be able to get bias and variance simultaneously to 0. So the regularization that can be applied, we will also talk about this later, is a way of increasing the bias and lowering the variance in return. So here are a couple of sketches just to illustrate this a little bit. If this would be the true function that you want to model, yeah, the measurements that you have are these, and if you look at them, they are a mess. Yeah, so there's a broad range of uncertainty, like what you're actually observing from the model. From your data creation process. So what model would be a good choice to fit to the data? And there's really no way to tell this. Like, you need a bit of information about your application or what you want to achieve. Yeah. In any case, if I'm showing you this is the ground truth function, yeah, then you have an oracle that tells you, I need to get something that somehow has this variation that looks a bit like a third order polynomial. So in that case, this first function here, this first function here is underfitting. No, it's not implausible, no, but it's underfitting. The second variant here is also not implausible, but it's overfitting. No? So, so we have a bit of we would need something that is a bit smoother than this overfitting case and a bit more variable than the underfitting case. And you cannot solve this out of the box. There's the so-called no free lunch theorem that shows that there's no universally best fitting model complexity. No, I think intuitively this also makes sense, but you have to tune this to the task at hand, the data at hand. Okay. So let's have this conversation about the bias-variance trade-off in the context of density estimation. So the density estimators, you could imagine to use them as primitive regressors or classifiers, yeah, by saying, well, okay, I can do regression by estimating f of x. So if f of x were a density, then I effectively already have something like a regressor. No? So estimate f of x at position x as a kernel-weighted sum of the neighbors. This would be a regression task with a kernel estimator. Or we could also say, well, we can take a mean of the k neighbors, and then we have a k nearest neighbor estimate of the value at hand. No? Analogously, we could define a classifier. So for the density estimator, it's a bit more complicated. We would say, okay, then we need labeled data. We have classes C1 and C2, and we can estimate a density for C1. We can estimate a density for class 2. And then at location X, we can return class 1 if class 1 has the higher density there, or class 2 if it's class 2. Okay. For the k nearest neighbor, it's even simpler. We just look at the k closest data points, check out their class labels, and do a majority vote. Yeah? Okay. So the bias variance framework, if we know this for regression or classification, then that way we can apply it also to our kernel-based or k-nearest neighbor classifiers, and we can observe that larger kernel support or a larger k for k-nearest neighbor increases the bias and lowers the variance. And conversely, smaller kernel support, smaller k, lowers the bias and increases the variance. Yeah? Okay. And having made this transition from our density estimators to the regression or classification tasks, we can also move the other way around, and we can say, well, let's transfer the notion of bias and variance to the task of density estimation by saying, okay, we have a too coarse or too fine estimate of our density, so the resulting density is too let's say undercomplex, or it's hallucinating structure. Okay, good. So that's all for today. We will continue this conversation in our meetings this week, and then in the future we will abandon pattern recognition. So today I mentioned pattern recognition quite a bit because I'm trying to sort of pick you up from there. At least those of you who attended that class, pick you up from there and continue with you from there. But then in the next weeks we will do like original, completely new content, mostly independent of the pattern recognition class. Thank you very much, and see you then in person in the meeting. Bye bye.